So here you have, we are looking at, let's say this is a two-way slab panel, okay, and you have this is the panel that we are considering, okay. The moment you know the column locations and beam locations, we are discretizing them as frames in the east, west, and north, south direction. Let's say that we have done. What we are required to do is we need to find the moments and design reinforcement in east, west direction of an edge end panel and an interior panel. So that is basically written as S1 and S2. Okay. And the floor consists of 6 panels, 9 meter by 8 meter panel. So 8 meter on the east-west direction, 9 meter on the north-south direction. Now all the panels are supported by 700 square columns. Okay. And it is also supported by beams with 350 by 750 cross section. Right. So that means 750 deep, 350 width. Now columns are all 700 square. In fact, column has to be shown as a slightly bigger because it is higher than the width of the beam. Okay. So these are all 700 by 700 and these beams are 350 by 750. Okay. And these are the dimensions that we're going to deal with. Now for these two edge panels, S1 and S2, we have to find out the distribution of moments and calculate what are the reinforcement that is required. So if you look at it in, let's say, the same thing, if you look at it in cut elevation, okay, so if you section elevation, this is how it is going to look like. So you have columns that are all part and the slab that is all part. In addition to that, you have these transverse beams are also part of the spray, right? So all of them is going to act. Now we are going to look at one such panel and then design for that. Okay, so let's look at now. What are the first we need to, before applying the provisions in direct design method, we need to check the limitations of direct design method. So the first condition is there should be 3 continuous spans in each direction. So in this case, if you look at it, and these are all what 700 by 700 right? And you see here, so what would be Ln? Ln will be 8000 because now we are looking at in the east-west direction. Okay, that is the direction that we are designing, right? So Ln is going to be 8000 minus 700, which is going to be 7300. That is basically your Ln. Clear span. Ln is clear span between the column faces, right? Now, what would be the transverse width of this particular frame? So you see from the column strip, you go to the edge of the middle next to this. So it is going to be L2 is going to be 9 meter because that's going to be your column spacing in the transverse direction, which is L2, which is 9 meters, right? Anyway, with respect to limitations, we have seen that you have span number 1, 2, and 3. So the first condition you are satisfied. 3 continuous spans in each direction. Next, the panels are rectangular with long span to short span is 9 by 8, which is 1.125, which is less than 2. So again, you don't have to get into the condition of your one-way slab. So the panels are rectangular with ratios less than 2. And there are no offsets. Here it's a very nice case where all the columns are in straight line. So there are no offsets. So we don't violate the limitations. Okay, and the successive span length should not differ by more than 33%. So you see here, each span is now 8 meter long. So there is no difference in span length. So that is also satisfied. Now let me assume slab thickness of 250 Now you can ask me, how did I assume this 250 we will tell you how to do that. So as a thumb rule, if you really quickly want to do, you can put L by 35 to start with. Okay, span by L by D ratio equal to 35 to find your effective depth. But let me assume 250 and I'm assuming a superimposed load of, let's say, 1 kilonewton per meter square. And then when you do that, you get a load of 7.25 kilonewton per meter square for dead load. Okay, this one is for superimposed dead load, right? Now, live load to dead load ratio, live load is given as 5 kilonewton per meter square. So 5 by 7.25 is less than 3. So I don't need to really consider pattern loading. And anyway, direct design method does not consider pattern loading. Pattern loading will become important when your live load to dead load ratio becomes more than 2 or 2.53. In this case, it should be less than 3. we are only 0.69. So live load to dead load ratio is very well within the limit. Now let's look at the next step is to calculate the relative stiffnesses of the beams. Okay, and the relative stiffnesses of the beams have to be between zero point 0.2 and 5. Okay, and now if you look at it, this relative stiffnesses is equation is alpha b1 into L2 square by alpha b2 times L1 square. Now what is alpha b1 and alpha b2? We have seen alpha b is IB by IS. Okay, and if you go back, so let's say, so for this particular panel, when you do it, so you consider, let's say this is your beam and this is your, so let's say for one panel, so this is your beam and this is your beam like this. So you consider your stiffnesses in two orthogonal directions. So that's what we're going to look at it, how to do that. So if you look at for the slab, one in the one direction, the width is going to be L2 and thickness is anyway ds. So width is L2, and you know moment of inertia for rectangular section is BH cube by 12, and H here is thickness of depth of the slab, which is ds. So ds cube by 12. Similarly, what is the span moment of inertia of slab in the other direction? Now in the other direction, the width is going to be L1. Again, depth remains same, so it is going to be L1 into ds cube by 12, and alpha b is IB by IS, and alpha b1 by alpha b2 will become IS2 by IS1, which now when you divide them, it will work out to be L1 by L2, because ds will get cancelled, 12 will get cancelled, it will work out to be IS2 by IS1 is nothing but L1 by L2. Now when you substitute that here, you will find that it will work out to be, this ratio will work out to be L2 by L. So that is will work out to be 1.125, which is between 0.2 and 5. So you are satisfying the relative stiffness requirements. Okay. So hence all the dimensions are satisfied, and we can use direct design method for doing the calculations. Now let us see what are the first step. Next step is in the two-way slab design. In any slab design, the slab designs are always, the thickness of the slab is governed by serviceability criteria, deflection criteria particularly. So we are in this case, to calculate the thickness, we are considering the critical panel to be exterior panel S1. So we are using ACR Canadian code for provision, which gives that the thickness has to be greater than ln times 0.6 plus Fy by 1000 divided by 30 plus 4 into beta times alpha b. Now what is beta? Beta is longer span to shorter span ratio. In this case, it's going to be longer clear span to shorter clear span, 8.3 by 7.3, which is 1.14. And Fy is, we are taking 500 grade steel, so we are going to take 500. Now, what is alpha BM? Alpha BM is the average relative stiffness parameter of the supporting beams to slab ratio. So let's calculate now what is alpha BM. Now, in a cast in place construction, the slabs and beams, everything is cast together. So we have seen in flexure also, a part of the slab will act as a flange for the beam. Now, if you're looking at an interior beam, so this much dimension. So if you take this clear dimension as, let's say, dw, then how much should be the width of the flange or the slab, portion of the slab that I consider that as a part of the beam will work out to be basically, if this is BW, I extend this by 45 degree, or in other words DW, and this side by another DW. So the total dimension at the top, I can consider that as a flange is BW plus 2 times the DW, or the the depth of your web portion, right? So, but anyway, this also should be less than BW plus 8 times the depth of your flange or depth of your slab. So, you have to satisfy this requirement. So, similarly for L section, it should be BW plus DW, and that also it should be less than BW plus 4 times the depth of your slab. So, like that, depending upon whether your column is or beam is an interior beam or an edge beam, I can consider that as a T beam or a L beam, right? So when you have a flat slab, again, depending upon what you have, beams width not less than column width, So in that case, then you will have only this portion, whatever that is within this column, will be considered that as a beam portion. Okay, this will be applicable when beam width is not less than column width. Okay, or when the beam width is going more than the column width, then what do you do? Okay, so that's what we are. Okay, so let's look at. So when you have a T section like this, from basic geometry calculations, you can find out the centroid, let's say from the bottom axis like this, as coming out to be this. Basically centroid calculation. So YC is this. And then when you calculate moment of inertia about this centroidal axis, you work out to be this simple formula using your parallel axis theorem. So you know you have studied in your basic mechanics of materials course. So I don't want to get into that. So you calculate depending upon the geometry, where is the centroid of the section, what is the moment of inertia about the centroidal axis, all those things. For slab and IS is going to be whatever the width of the slab in the transverse direction, and depth is going to be d. So it is going to be again L into d cube by 12 will be your moment of inertia of your slab. Now once you get your IB and your IS, then alpha is nothing but ratio of IB to IS. Now what is IB? IB is the second moment of area with respect to the centroidal axis, and IS is LD cube by 12 is the second moment area of the slab. Now you can also do the same thing for an edge beam which will be like an L shaped, right? So you can do all those things. So now let's look at this exterior panel S1. Okay, and because why are we doing this? I need to use to calculate the thickness requirement to satisfy deflection criterion. To calculate thickness requirement, I need to find out alpha BM parameter, which is the relative stiffness of all the beams that are supporting this panel. For example, I need to calculate alpha for this, alpha for this, alpha for this, alpha for this. Now this beam will look like a T section, right? Now this beam will look like a L section, right? So similarly, this and this will look like this, right? Similarly, this also. So only this edge beam will look like an L section. So depending upon the geometry that we have, alpha B parameters have to be calculated. Now what is A? A is for this. Okay, let me erase this. So this is for the first case A, and these are the dimensions. Then you calculate your moment of inertia of beam, moment of inertia of slab, and then you get your alpha parameter is 3.3. Similarly, we go ahead and do for this. Next is case B. Okay, A2, B2, and A3, B3. So that is this is also same. So this is also case of B. Okay. So like that for this also alpha works out to be 1.8. Similarly, I do it for the this location which is C. Okay, and alpha works out to be 2.06. Now I need to calculate, and similarly for slab beam member along A2 and B2, and you will find that it is going to be this. Okay, this is this. Okay, so you get ISB as 3.8 into 10 to the power of 10, and I slab is this. So if you substitute that, you get your average. What is alpha beam? Alpha beam is the average value of alpha beam for all the beams on the edge of the panel. Now we calculated alpha B of 3.39 for transverse beams at exterior support, 2.07 for transverse beams at interior support, 1.88 for long tail beams at exterior support. So you take average of all those things, you work out to be 2.285. Now in this formula, alpha BM cannot be greater than 2. So if you substitute that, and LN is a longer span, 8.3 meter, times 0.6 plus Fy by 1000 divided by 30 plus beta 4 into beta, which is your longer clear span to shorter clear span, which was 1.14, and alpha BM. In this case, everything is greater than 2, so we limit it to 2. If you substitute that, you get thickness or the depth of the slab should be at least 233.4 mm. Then only deflection criteria automatically will be satisfied. Otherwise, you have to explicitly do the calculations, and deflection calculations for a two-way slab is quite involved, so it is relatively difficult. Rather, we can do finite element analysis and find out. So, but if you use this, you don't need to explicitly check Okay, so the slab thickness of, we can say, now when you put 15 clear cover, and then let's assume that 8 bar we are going to use, or 10 bar we are going to use, then it will work out to be that 250 will be adequate. Now also we can see that when alpha b times L2 by L1 is greater than 4 for all the beams, okay, so they are adequately stiff. So in fact we don't really need to use the direct design method for this particular example. We could have actually used moment coefficient method that is given in your IS 446. That also would have been more conservative. In fact, those coefficient values are higher, will be conservative than what is given in your direct design method. Okay. Okay, so now that we have checked all the limitations, we have calculated the thickness of your two-way slab. And now we'll get into the determination of moments. What are the three methods? First method is for all the spans, I need to calculate total static moment, and then I need to get longitudinal distribution of moment, and then I need to go for transverse distribution of moment. Now let us calculate total static moment. Now you see on the Ln is 8,000 by sorry, this should be, yeah, 8,000 minus 700, so it is going to be 7,300. So total static moment is W times L2 times Ln square by 8. When you substitute that, you get a moment of 1,102 kilonewton meter. This is a total static moment in that span. Okay, and how do you get your W? Again, 5 is your live load, and 1 is your superimposed load, and this is your thickness of the slab. So when you add all of them and multiply by 1.5, you get a factored uniformly distributed load of 18.375. So when you substitute that, this is what your total static moment is. Now let us look at what are the longitudinal distribution moments. It's very relatively very easy. We are just going to follow this coefficient. That's all. This at exterior span, exterior support, this is the value. At exterior span, mid span, this is the value. At exterior span, interior support, this is the value. So like that, you just follow the coefficients and you find out what are the distribution. Now, so for example, M0 we have already calculated. To use this, now I need to just find out what is Q. Now what is Q? Q is 1 plus 1 by alpha C, where alpha C is summation of stiffness of all the columns that are connecting at the exterior joint divided by flexural stiffness of the slab beam. So this is the one that we calculated in the previous case, the slab beam element. Okay. So you plug in these values and you get your Q value. Okay. And then you can calculate alpha C. And let's see now longitudinal. For interior panel, it is very straightforward. 0.65 times, this is your M0. Okay, 65% of your M0 goes as a support moment here, and 35% of this goes as the positive moment. So it's very straightforward. Now for exterior panel, let's look at it. Exterior span. Now because I need to find out what is Q. What is Q? Q is 1 by alpha C, right? So sigma Kc is, you have column above and column below. Now, what is the stiffness of the column? 4A by L, 4A by HC, where height of the column, right? And you have one below and one above. So that's why I'm multiplying by 2, right? Now, what is the stiffness of the slab beam that is connecting? 4E ISP by L1. L1 is the span, right? So when you simplify that, alpha C works out to be 2 into IC into L1 by ISP by HC. And if you substitute your values, then you get your alpha C as 2.39 and Q will be 1 plus 1 by alpha C. So we substitute Q is 1.4. Now that I got the Q, now what is the distribution for your exterior moment? 0.65 M0 by Q. So that works out to be 0.457. 0.457 times M0, which is 1102, then it is 504. So that is what I have written, 504 kilonewton meter, right? Now, what is the negative moment at interior support? It is going to be 0.75 minus 0.10 by Q times M. If you substitute for the Q that previously we calculated, that works out to be 0.679. Then that value is 749. So that is what we have written here, right? Now, what is the positive moment at the interior support? Or sorry, this should be, yeah, what is the positive moment at exterior support? Okay, so 0.63 minus 0.28 by Q times M0. So that works out to be 477 kilonewton. That's what we are getting. So all these values are for exterior span. Interior span we have already got 0.65 M0 and 0.35 M0. This is 716 and 386. For rest of the things anyway, they will remain same. Now, you can also see that pattern loading we no need to consider because live load to dead load ratio is less than 3. So the second step is over. That is calculation of your longitudinal distribution of your moment. Now, it is a two-way action. We have seen column strip should take majority of all these moments, and middle strip should take only portion of that. Because why? Column strip is a stiffer region. Stiffer region should attract all this moment, right? So that's what the next step is, the transverse distribution of your moment. Okay. So at each critical section, now the part of the design moment will be assigned to the beam and balanced to the slab portion. And in this case, because it's a two-way action, again, we have to make sure that the beams are going to also take some portion of the moment. Okay. So the fraction of the positive moment in all the spans and negative moment at the interior columns to be resisted by the beam, which is given by this parameter. How much should go to the beam and how much should be retained by the slab. Okay. So that is this parameter alpha b1 by 1 plus L2 by L1 the whole square. So if you substitute it, it works out to be 0.44. And now alpha b1 cannot be greater than 1. So alpha b1 here, if you look at it, it works out to be 1.81. So hence the moment share, in this case, it is 0.44. Okay, the moment share of the slab is only 56%. That means of all the longitudinal distribution moments, okay, slab is going to take 56%. Remaining has to be given to the beams. Okay, how much? It is 44% to beams. Remaining 56% should be given to slabs. Okay, because it's two-way bending. It is also, slabs are also deformed, the beams are also deformed, right? So that is also going to take some. Okay, at exterior support, the beam must be designed for 100% of the exterior moment, and no moment should go to the slab. This is the procedure that is given by direct design method. And also the reinforcement shall be placed within the bandwidth of BB, which is equal to 1350 millimeter. And the factor design moments in S1 and S2 are, now we can look at that finally. Okay, so this is what we got. Okay, so if you look at it, this is the longitudinal distribution, what we got. Okay, 504, 477, 740. Now in this thing, we are saying that beams are going to take 44% and slabs are going to take 56%. So every location 504, only at the exterior moment at location, all this 504 should be taken by only beams. Okay, but all other locations, the moment share for the beam is only 44%. For slab share is going to be 56%. So I multiply by 0.56 all those things, and then I distribute this to slabs on either side. Okay. So if you look at it, one value 477 multiplied by 0.56 will give me 268. That 268, what I'm doing, I'm putting it to the slabs on either side. Okay. So that is what we do. Similarly, we do it for 386 also. 386 multiplied by 0.56 will give me 260. So this one side and that one side. So like that we distribute, because this beam is also part of this, that is going to take some moment. Okay, how much moment we will give it to the beams? That is what we have done based on the relative stiffness of the beams. Okay, so when you substitute all these things, now that we got these moments that need to be designed for the slabs, okay, so we can go ahead and check what is the panel moment demand that we're getting. Now, effective depth of the slab, if I assume 20 mm cover and 10 mm bars, it works out to be 225 mm. Similarly, for beam, it works out to be 699.5 mm. Then you can get your R value as mu by BD square at different locations. Mu is negative 504. R is 2.94. For positive moment 210 kN/meter, R works out to be 1.23. Like that, different R values to calculate the flexural demand can be calculated for beams as well as for slabs. Now slabs at the exterior support, it is not going to take any moment, so I don't need to worry about it. All the moment is going to go to only beam. Similarly for slab, it is 0.69 R values, 1.08 and 0.557 at different locations, right? From all these things, we can calculate your steel requirements. And we should also make sure that the steel, whatever that we calculate, should be greater than this minimum requirement of steel for beams, which is 0.85 BD by F5. And for slabs, it should be 0.0012 or 0.12 percentage of your BND. So once we calculate all of them, then once you basically what we have done in direct design method is we have done analysis and we found out the distribution of moments at various locations that need to be used in for calculating the steel reinforcement. That's all, right? So the flexural reinforcement in slab and beam. Okay, so the negative moment reinforcement in the beam at the top must be spread over a width of 350 plus 1.5 times ds. Okay, on either side. So that's how we end up with this location 1350. Okay, how did we get this 1350? Basically, it should be spread over 350 times 1.5 times ds on uh, this. So if you substitute that on either beam rib plus width of the slab, 1.5 times ds by 2. Okay, on either side. So that is the reason we ended up with this 1350. And there is no negative moment to the slab part of the exterior support. However, the slab at this part have to be provided with minimum rate that we said. At the exterior support, at the exterior location, exterior span, the beam portion has to take all the moment. Slab will not take any moment. However, some minimum reinforcement has to be put. So, although mu is 0, in order to take care of positive and negative moments due to partial fixity, it would be appropriate to provide top reinforcement equal to 50% of what is provided at the midspan, extending 0.1 L. So, these are detailing requirements. Okay. So, though slab is not required to take any moments, you don't need any reinforcement, but as a good practice, as a good detail, whatever the positive moment reinforcement that is coming, that you take 50% and then you put it. And all the positive moment reinforcement perpendicular to the discontinuous edge should be extended to the slab edge and embedded as per the clause 31.7. These are all some detailing requirements. Now you can also see as the beams are torsional reinforcement also we have to check. Okay, and especially the edge panels. Interior panel it will balance. Okay, in the edge panels and corner panels we have to check. Okay, so now in this case the supporting beams are adequately stiff, so torsional reinforcement has to be provided at the corners at discontinuous edges in panel S1, as in the case of wall supported slabs. And the requirement is 0.375 times AST plus. In the present example, it works out to be 125 mm square per meter. Then you can put over a square size of 0.2 times E, which is 1.6 meter. So this side 1.6 meter in the corner. This has to be provided in only discontinuous edges. That means the slab is not continuing on those sides. Only there the corner will lift up. But when it is continuous, it will balance. So there is not going to be any lift up. Right? And also we have to see the beams are provided along the column lines. We also need to be careful about how we are transferring the moments to the column. Especially in flat slab, it will become very important. In this case, beams are provided along column lines. So transfer of unbalanced moment to supporting columns is not really critical. And usually the largest unbalanced moment occurs at exterior support and the beam is actually designed to resist this input. Okay. And as per the requirement of clause 31.33, the moment transfer between slab and column through flexure is a primary concern in flat slab because flat slab there is no beam. Everything is getting transferred directly from slab to column. If your span on the either side of the column is quite large, then you will have unbalanced moment that we need to be transferring properly. So that unbalanced moment also, how much will transfer in bending and how much will transfer in shear is determined by this parameter called gamma. Okay, and gamma times mu, the demand at that location, will be the moment that I need to transfer through flexure. And 1 minus gamma times mu is the remaining portion that I have to transfer through shear lengths. Okay, so this especially will become important when you have a flat slab. Why is it is coming? Because a moment on the left and right side of the column is going to be, or a slab is going to be different. Okay, this is M1, let's say this is M2. Now M2 is greater than M1, the difference has to be somehow transferred. How much you can transfer that in flexure, how much you can transfer that in shear will work out from this gamma parameter. Okay, again, shear in slabs and beams also we need to take care of that. All the beams in this example are adequately stiff, so they shall be designed to resist full shear from load that is coming from tributary areas, and slabs have to be checked and designed for one-way shear like this, and we need to consider a 1 meter wide strip and distribution and check for design shear at critical section D from the face of the beam, like what we do for typical one-way shear. So that also we need to check. Okay, so if you look at for this particular example, the shear demand is WU times 0.5 ln minus D, and this is your factored load, and ln is 7.3 and D is 0.225, so that works out to be shear demand of 62.94 kilonewton. Then your nominal shear is shear demand divided by breadth, which is 1 meter, divided by effective depth, which is 225 millimeter. That works out to be 0.28 megapascal, which is should be less than tau max for a particular grade of concrete, which is the case here. And for slab, the shear strength is K into tau C. And for M30, the amount of steel that is provided is 0.279 percentage. For that, if you look at your table, you get your tau C of 0.385 megapascal, which is higher than your demand, which is 0.28 megapascal. So K into tau C is greater than tau V, so it's okay. So this is we are assuming 10 mm bar at 125. Okay. So all the beams in this example are adequately stiff. The slab system may be adequately designed by much simpler method of moment coefficients prescribed by code supported for wall supported slabs. In this case, actually direct design method we may not have used, but just to illustrate the concept of direct design method, we have adopted this. Because these beams are very stiff, we could have used moment coefficient method. So that is it. So let's summarize what we have done. So we've discussed the limitations of the code coefficient method for design of slabs, and we discussed the procedure for design direct design method, and we also discussed the limitations and applications of direct design method, and we also went through one example in detail for one couple of edge panels that we use this method to calculate the moment distribution. Once the moment distribution is found, calculating reinforcement is a straightforward process. That's basically section analysis, right? So these are some of the useful references, and with that, I would like to thank you and will also acknowledge the help of my PhD student, Mohan Krishna, for helping me with this presentation. Thank you.